Introducing Pinocchio1B, a reasoning model built for the Kaggle Tunix Hackathon. Using Tunix, a JAX-based post-training library, I transformed Gemma 3.1b into a reasoning model that shows its work in a single Kaggle session on TPUs. Let me walk you through the complete pipeline. Pinocchio is created by 3 sequential training stages. Supervised fine-tuning, SFT distillation, builds the reasoning foundation. Simple preference, optimization, SimPO, aligns format and style offline. GRPO uses reinforcement learning to optimize the final capabilities. First, we built NoseCheck, our LLM judge powered by Gemini 2.0 Flash. It scores correctness, reasoning quality, answer quality, plus 11 fatal flaw flags and 8 positive rewards. We chose Gemini 2.0 Flash for speed and cost. 2,000 requests per minute, processing 1,000 evaluations in under 60 seconds. Base Gemma scored 57% accuracy with many fatal flaws. That's our baseline. Why start with SFT? 4 reasons. Stable starting point, compute efficiency, explicit instruction for small models, and foundation for optimization. We want Pinocchio to reason across any domain with just a user query. Creating the SFT dataset was the hardest part. There's not much free, high-quality reasoning dataset that exists within the context length of interest, so we built one from scratch in 4 phases. Phase 1. Collected 70,000 prompts across 17 domains. Phase 2. Used GPT-OSS 120 billion as teacher. It's a top open-source reasoning model that provides raw reasoning traces and lets us customize the reasoning length and effort. We passed all prompts through it, constraining generation length. Phase 3. Adding virtual MOE. We classified responses into 34 task categories using Gemini, then prepended this is an XYZ task to each reasoning trace. This helps the Pinocchio root its thinking and branch learning. Phase 4. Quality filtering. Multi-layer filtering ensures only high-quality examples make it to training. NoseCheck scored teacher response. Dropped anything under 8 out of 10. We used Tunix's SFT trainer with custom precision masking. Standard SFT calculates loss on everything. We only calculate loss on output, not the prompt. Trained for 3 epochs, 9,135 steps with a runtime of approximately 2 hours. SFT evaluation results show significant improvement. Average accuracy jumped from 57% to 72.2%, a 15% gain over base Gemma, with high reasoning quality and format adherence. We saw dramatic improvements in complex logic domains and in non-verifiable domains. In trick questions, we improved from 23% to 72%, proving Pinocchio thinks before answering. There's an alignment tax though, math and code dropped slightly. A 1B model has limited parameter capacity. By optimizing for reasoning structure and reliability, we inevitably overwrite some parameters previously used for rote memorization of facts or syntax, and we traded that for reasoning reliability. The massive gains in accuracy, format adherence, and reasoning quality far outweigh this. Step 2 is simple preference optimization, SimPO. Think of SimPO as a strategic bridge between SFT and reinforcement learning. Why not go straight to RL? GRPO is powerful but limited in a 5 to 6 hour run, and we can't control sample quality generation. SimPO is stable, lightweight, and eliminates sampling. It does in 30 minutes what GRPO would take hours to achieve, sometimes even better. SimPO has 3 advantages over DPO. First, memory efficient, requires only 1 model, freeing HBM for larger batch sizes. Second, fixes the length hack, it divides by response length, rewarding conciseness and quality density, not fluff. This is vital for clear reasoning. Third, performance. SimPO often outperforms DPO by optimizing the generation metric directly. SimPO dataset creation uses an off-policy data strategy. 2 dataset types. Polisher set, student versus student, scored by NoseCheck. Corrector set, high-quality teacher versus failed student. This teaches preference and hard corrects errors. Tunix doesn't have a custom SimPO, so we modified the DPO trainer with custom loss function as shown here. Key technical decisions. First, length normalization prevents the model from gaming rewards through verbosity. Second, label smoothing with alpha equals 0.1 acts as a safety valve. It adds a custom term that prevents the model from becoming arrogant and destroying SFT weights when trying to maximize the probability gap. The policy model was initialized from 64 rank LoRa weights from Pinocchio SFT checkpoint, a slight 0.5% improvement in accuracy over SFT. Although SimPO improved format accuracy on creative domains, format accuracy dropped 1%. The major culprit is math, where format dropped from 98% to 91%. Almost all looping issues where the model generates incoherent repetitive tokens. This happened because we're forcing the model to emulate teacher outputs it can't replicate due to capability limits. Otherwise, we have improvement in format adherence in most other domains with slight accuracy gains. We'll fix the looping issue in the next GRPO run by designing it as a major penalty in the reward signal. Step 3 is GRPO. With approximately 5 hours left in the session, a comprehensive curriculum learning approach wasn't feasible. Our strategy? Create a highly efficient reward signal to reduce hallucination and factual errors. Teach the model to avoid looping or incomplete outputs, ensure format consistency, and improve correctness with better reasoning and answer quality. We have a rubrics-based reward system, powered by our NoseCheck LLM judge. The whole GRPO setup as well as the reward function is explained here. We ran GRPO as a LoRa policy for 800 steps, with 8 generations and a batch size of 2. Number of iterations was set as 2 to improve convergence speed. The run stat logs show clear improvement. Total reward shows a clear upward trend as the model learns. With GRPO, accuracy and quality improved slightly. The notable change is the improved format accuracy. We're up to 98.7% with incomplete flaws reduced by 50% across most domains of interest. This was a GRPO run on a maximum of 800 steps. Ideally, if we ran with a curriculum learning strategy using different reward signals across much longer time and steps, we could improve the model further. With this LLM judge-based rubrics as reward system, we now have the capability to design rewards by describing what we want to improve, while retaining speed and efficiency. It's as easy as describing what the rubric should be in the NoseCheck prompt. There we have it, our thinking Pinocchio1B. 3 stages, 9 hours, 1 reasoning model. The complete Kaggle notebook, all datasets, and the NoseCheck Judge implementation are publicly available. Thank you for watching, and good luck with your own reasoning models.